All right. Hi, Verge.
Hi, Mark. Welcome to Wednesday.
It is Wednesday. That's a good thing.
You didn't wear pink.
No, well, not that you can see. Um, Socks. I have lots of pink socks. Um, I don't know. There may be some pink on this mess of a. It's Guardians of the Galaxy Hawaiian shirt. It's all right. So, I am Mark Corelli. I'm from Ryan High School in Denton, Texas, and you are here for AB Calculus. We hope.
And Verge Cornelius from Lafayette High School in Oxford, Mississippi, here to do a little calculus with everyone. Let's get it on.
Jeez. All right, we're starting to streamline some of these slides that probably cause our ratings to plummet. This is a Unit 8. We're in the middle of this week. I know we're going to have our mistake page in a second, and this said starting today on Tuesday, but we're not counting that. We're looking for mathematical errors. So, okay. And then next week we start our review leading up to May 1st, so we can all get ready for that May 12th exam administration. Verge, is this your slide?
Sure. The only thing we changed on this slide was that we made the correction that it says online 45-ish minutes because we didn't know how they were coming up with the 45, given that it was 25 plus 5 plus 15 plus 5. No matter how I do that, it kind of ends in 0. But anyway,
optimistic about these 5 minutes, maybe. I don't know.
Yeah, something like
Small
that.
values of 5 minutes.
Yeah. So anyway, that's the same slide we've been showing for a few days now. This slide looks the same, but it is not. This is exciting.
We're up to 6.
6 consecutive days without any mathematical errors. Although I must say that I did make an error in that problem where Mark had gotten 31 and I had gotten not 31. I went back and actually found my mistake, which took a while. It's always very convincing when you're looking at your own work. It's hard to find a mistake.
That's what good students do, though.
Thank you, Mark.
Well, I always tell in a likewise thing. I'm sure organized work is very hard to find mistakes.
Oh, well.
So, okay. So since we haven't had many corrections, we made a slight change here. And we've also cleaned this up. The guided practice, you guys know the guided practice and lesson are rolled together now at this point. If you've been here once. So
and
we're gonna have our warm up.
That being said, whenever we are working a problem, of course you should pause it. Even if you're watching live, you have the capability to pause, work it on your own, and then tune back in and see, compare your work to our work. So
absolutely. And so we've got our warm up today, and then we were going to talk about 8.3. And Verge, do you want to? First, I'll read it the way it's written, and then you can possibly translate using acfunct and defint in app contexts.
Yeah, this is called Mark wants to get the entire thing on one line, so he abbreviated it all. 8.3 is using accumulation functions and definite integrals in applied contexts. And given what we did yesterday, ACC could be acceleration. So I did a good job there.
Oh, yes. And an app could be applications or applied, right? So 4.3 is what we're going to tie back to today, which is rates of change in applied contexts other than motion. And 6.5, interpreting the behavior of accumulation functions, right, involving area. So here's today's warm-up, and we are tying back to, I believe it was problem 6 yesterday. Is that correct? Or was this? No, I'm sorry. This was one of the free responses. This was one of the FRQs.
This was one of the free response. That's yes.
Right. And so this was the one we finished with yesterday, right around, I don't know, 2:47 Eastern. Let the velocity of q of t be equal to t squared minus 8t plus 15. And that is the velocity of particle q. Now we've added some context for you. So in miles per hour and 0 to 8 where t is measured in hours. And we would like you to interpret the following in context using correct units. So 2 of these are, the first 2 are values we found yesterday. The third is a extension. So a sub q of 2 is equal to -4. The integral from 0 to 3 of v sub q of t with respect to t is 18. And 1/3 of the integral from 0 to 3 of v sub q of t with respect to t is equal to 6. And we'll give you a few seconds. You can pause it to try to interpret each of those in context using correct units. And for those of you that don't want to pause or already have it done, Virgil, kill some time here.
Well, I just want to let everybody know that yesterday we have our meeting before the live session with our producer, and then the meeting after the live session with our producer. And by the time we were kind of wrapped up at the end of that, and I checked my email, I had gotten this lovely image in my email from a student in Wisconsin who, this was the first person to send me anything. Okay, this person was the only person to send me anything. But anyway, look at those Mobius strips, how beautiful they are. There are 5 Mobius strips there, and you can see the twist. And then she's attached them together with tape. So anyway, I think one thing that I do want to talk about is I have a loop right here. And what I'm going to do with the loop tomorrow is I'm going to cut this loop. And this is not a Mobius strip. I'm just going to cut it all the way around and see what happens. You could maybe imagine what happens. And then think about, what's going to happen with those the Mobius strip? Same thing or maybe something different? Okay. All right.
Safe money is on something different.
Something different. That's why it's so cool. Yeah.
All right.
Okay.
So interpreting these, you want to take a shot or you want me to take a shot?
I'll take a shot. I'll do the first one and then you can do the next 2. So
excellent.
A sub q of 2, this would be the acceleration of particle q at time t equal 2 hours, and that acceleration would be -4 miles per hour squared, or miles per hour per hour. I think you could also say something like the velocity is decreasing at 4 miles per hour squared when t equals 2, something like that. Now, don't write that stuff down, folks, because we are going to show you a slide that you can actually access in our shared folder of these verbal descriptions, interpretations.
And so I guess I'll take the second one. And also, not only do you not have to write them down, because we're going to share these as a slide. And sorry, I was checking. I'll be honest, I was looking at my phone. I don't think I've actually got the slides ready. I'll put those in the Dropbox after the lesson. The assignment parts are in the Dropbox already, but I'm holding back keys until after. So.
How nice. Okay, good.
So the integral from 0 to 3, this v sub q, as we set up here, that's the velocity. So we are integrating velocity. When we integrate velocity, we find displacement. So this is going to tell me how far the particle is from where it was at time 0. We did know that yesterday, but in this context, I don't. So this is telling me that from time 0 to time 3, in the 3 hours from time 0 to time 3, the particle has moved itself 18 miles to the right of its original position.
Good.
And then dividing this by 1/3, this actually
multiplying by 1/3.
Well, I'm sorry, you're right. Yes, dividing by 1/3 is the same as multiplying by 3. Dividing it by 3 or multiplying it by 1/3 obviously makes it a 6. But then when we do a unit analysis, this velocity is miles per hour, dt is hours. So that's why we get miles when we look at that as a product of units. But now I'm dividing by this 3 again, which came from the width. So this is miles per hour again. So that 6 miles per hour represents the average velocity of our particle q from time 0 to time 3 hours.
Nice.
And let's see how we did. Yay. So, and again, these slides just straight up as a PDF will be in the Dropbox after the lesson today. So.
And this is something that we wanted to start with because we're going to circle back around to it as we work on this next section. Things in context is really what we're about, but we also are going to examine the accumulation model somewhat with and without context. At first, we're going to examine it without context and then get more and more into the context.
Yeah, and specifically its context other than velocity. The velocity model is what we really want to look at. So this is a warm-up brush up of last time, but you can see how we're going to extend it.
Yep. Okay, so should I grab the screen, Mark?
Time for you to grab it, yeah.
Okay, we're getting into a routine here. It's kind of funny. Okay, let's see what I can do. And it worked. Yay. Okay, yay. This is our 11th live session. Thank you all so much for joining us. And it's Wednesday, not that that really matters, but whatever. Okay, anyway, we have a wonderful set of exercises here that Mark wrote maybe a year or two ago. I can't
Yeah,
remember when you
I think it was
actually wrote
last year,
this.
but I'm not positive.
And this is a circuit called accumulation models. And so what we're doing here is we are using the accumulation model to find out a missing value, basically. Sometimes it's a very generic version, no context at all. And other times there's a word problem or something like that. I'm only going to do 4 of these with you and then turn it over to Mark, who's going to do some other problems. But this will just kind of get us into the mode. And these are great problems. If you have your calculator, lots of them are calculator active. We'll see how mine does. Stop freaking out there. Okay, well, anyway. The first one says, given f of 2 equals 5 and f prime of x is equal to x plus sine x, find f of 4. These are the kind of problems that a lot of times my students, when they first see them, go, what are we supposed to do? And the thing is that if you think about, and I'm going to be very generic right now, in fact, so generic it's fundamental theorem of calculus, the integral from a to b of f prime of x dx is equal to f of x evaluated from x equals a to x equals b. So it's f of b minus f of a. So this is fundamental theorem of calculus right here. And I can use these parts and substitute into this theorem, this formula. So my limits of integration are going to be 2 and 4. So I'm going to think about the integral from 2 to 4 of my f prime, which is x plus sine x dx, is equal to f of 4 minus f of 2. So I know that f of 2 is what I'm looking for, or sorry, f of 2 is what I have, that's 5. F of 4 is what I'm looking for. And then this right here, I can use my calculator and I can use a function that on my calculator, I just say math 9, and my students usually know what I'm talking about. I like to load my function into my Y1 before I do that. But then I just go to my home screen or my clear screen and hit math and then 9, which pulls up this, it's getting blinded by the light, pulls up this definite integral right here.
Ferg,
yes, sir.
Just a pro tip with dealing with light glare. If you have a 1/4 inch of sticky notes and you put it under one side of the calculator, it'll clear. Just put it right under the one side of the calculator.
Well, that's worse.
See, and I
You
can't
mean
see
because
yours.
the glare gets adjusted?
Yeah,
Okay.
it'll just angle it. There you go.
Better? Okay. In any case, well, sorry about that. I was going to show something else.
Sorry.
No, that's okay. I was just going to call up, I was going to do alpha trace and call up the Y1, and then that way I don't have to retype it. Like if I've looked at it for some other reason, or you can type in the x plus sine x. Again, make sure you're in radian mode, but you know, I never go to physics class, so I'm always in radian mode, but some of you who go back and forth, you need to make sure that your mode's in radian mode. But I got 6.237. So 6.237, and then 4, it's an intermediate value, so I might go ahead and use more than the 3 decimal place precision that AP usually uses. And if I add 5 to both sides, I end up with 11.2374, which, oh my gosh, happens to be that answer right there. So that reveals the second problem, which is another problem with the same idea, where I'm going to use, the way I think about it is using that fundamental theorem of calculus to set it up. So let's see what this one says. A particle moves along a straight line and its velocity is modeled by v of t is equal to 30t minus 5t cubed. The particle's position is modeled by s of t, and s of 0 is equal to 4. So that's like going back to yesterday, the relationship between velocity and position is that the integral of velocity gets us the position, the derivative of the position gets us the velocity, and that kind of stuff. So find the particle's position at time t equals 3. That's going to be one of my bounds, and the other bound is going to be 0. So the integral from 0 to 3 V of t dt is equal to S of 3 minus S of 0. Looks a little different than before with the primes and everything, but it's the same exact idea. So here, let's see what I have. I have S of 0, or I can substitute that in. So I'm going to be adding 4 to whatever I get here when I evaluate it. And this one's actually, yeah, this one's actually not that bad to do by hand, but because it, you know, Mark said, let's just go ahead and use the calculator. That's fine. I know
this is one of the units where this is one of the units where I first really start using the calculator heavy. So it was to force my students to start mastering that skill.
Yeah, that's a good point. I do that definitely with volume. Is I definitely start, because we don't use calculator much at all in my class until like after spring break, which here we are after spring break. Okay, so I think I typed that all in properly.
That's
and
good.
Then okay.
You misspelled T, but
Oh yeah, but we can tilt it, right? All right, so I got 33.75. And if I add 4 to that, I'm going to get 37.75. And I would search for that answer. If you haven't yet done a circuit, that reveals the next problem. So the next problem is actually right here. I did these already at like 6 this morning, so I numbered them all as I went. So easy for me to find. All right, so this next one right here is a no calculator, so put that to the side. The graph of G is shown. F of x is equal to the integral from 1 to x of G of t dt. This is really important information. AP will do this all the time, show the relationship between F and G, or maybe F and F prime or something. And you'll see as we review for the AP exam, we'll bring in a lot of kind of problems that deal with that. G consists of a quarter circle and 3 line segments. So here's our graph of G, a quarter circle and then 3 line segments. And our question is, can we find F of 3? So F of 3 is going to equal the integral from 1 to 3, substituting in a 3 up there for the x, of G of t dt. And so this right here, the integral from 1 to 3 of G of t dt, is actually going to be the area between the function and the x-axis, or the line y equals 0, from x equals 1 to x equals 3. So this triangle right here, and it truly is a triangle. He told me that these were 3 line segments, so I can't be like, well, it looks like a triangle, so that I do. This is going to have an area of 1 plus the other triangle is also going to have an area of 1. I don't know, Mark, do you feel like we need to say how I'm getting that 1 there and the other 1, or are you good?
I think half of 2 times 1 is pretty obvious.
Yeah, so this is 1, this is 2, exactly. Okay, so 2 is my final answer there. In any case, I'm not going to do number 4 for the last one. I'm just going to go ahead and skip to one of my ones that I wanted to do in the first place, which was number 10. And I kind of wanted to do this because I feel like this is my life right now. And let's see why. In number 10, it says, a printer is publishing multiple copies of a specific document. While printing this document, ink is being used at a rate of RT equals 0.2, and then parentheses 1 plus cosine of pi x, close off the parentheses, measured in ounces per minute. If the printer started the job with 5 ounces of ink in its cartridge, how many ounces of ink will remain in the cartridge after 3 minutes of printing? Now, I might jinx myself right here, but every time I go to print something on our printer, it says ink is low. And then I hit okay, like, what am I going to do about it? Like, I can't go get some ink right now. I just keep hitting okay, and it keeps printing. I'm not sure how that's happening, but anyway.
It doesn't say ink is empty. That's right.
That's right. And it doesn't say cannot do or something. It just says okay, and I said okay, so I click it. In any case here, this is the rate at which the ink is being used. And so if I really want to find the amount of ink that's being used, I would have to integrate the rate. Because that really, think about the units. If you have, this is in ounces per minute, and if you integrate, you're multiplying by minutes. So let's see here, the integral from 0 to 3, those are my minutes of my R of t dt. This right here is really minutes times this right here is ounces per minute. So I will know how much I have used up when I figure this out. And then I think I need to then subtract that off of the 5, because the question is really how many ounces of ink will remain. So I'm going to go ahead to my calculator because it says I can. Well, let's try this little sticky thingy.
While you type, I'm just going to throw out a nugget because students in my class know that they're going to leave with information that has nothing to do with calculus. Ounces. Do you know why the Z's there?
No, but like, look at that. I crossed my Z. Did you cross your Z's?
It's from the Greek word for ounce, which doesn't have a Z, but used to.
Huh.
So I thought
wow.
that was cool.
And we were talking about
it is from the origin language, but even in the origin language, they've lost that letter.
Wow. Yeah, we were talking yesterday about like dicot in biology, the di means 2, whereas in math, a lot of times we say like binomial, where the bi means 2. Of course, English came out of Latin and Greek. So all sorts of fun ensues.
And some Germanic. Don't forget. Not
to mention all the.
Don't let our Northern European friends out of the mix. That's
true. Okay, so I'm getting 0.6. So it seems like since that's equal to 0.6 ounces, then 5 minus 0.6 would be 4.4 ounces remain. And if I look to where I said number 11 was at 6:30 this morning, there it is, the 4.4, and now I'm opened up to a new problem. This would be an excellent set of exercises to do. My students didn't do these problems yet this year. It's a good set of exercises to do, and my students can definitely expect one on their quiz this weekend. So there you have it. Okay, go ahead, Mark. You're going to go ahead and grab the screen.
Yeah, and I'm actually I'm going to start with hopefully something relevant. Oh, my Zoom controls have disappeared. That's cool. All right. There they are. Okay. And then it asked, "Are you sure you want to take it?" And I said, "Yes." All right. So Verge was doing all these accumulations with Fundamental Theorem. Yeah. Part 2 or 1, depending on your book. But I just want to say, and I love this because I'm sure Verge's in the same camp. Even with the yellow sheet, you want to memorize as few things as possible. But one of the ways I also do this is the traditional accumulation model, where you take f of b and then add f of a to the integral, which is what we're doing so much in these.
Which makes so much sense. Yes.
I mentioned the Taylor form of the point slope that I use last week sometime, right? Where I moved the y naught over, and so the y sub 0 plus m times x minus x 0. And then, of course, when we're doing a tangent line, this is delta x, and that's f prime. But if you look at the parallels here, this is the new y. This is my function value at b. My initial value, the value I know, my f prime, and then my change in x. And so just so cool how all of the stuff we do works.
Yeah, and I would say too, like when you're looking at that, well, don't move it too fast, but basically I'm starting with a value, and then I'm figuring out my new value by adding a little bit to it, and I'm going up and over by this amount or whatever. So like both of those, that's what it's saying.
Right, exactly.
I'm starting here.
It's almost like they're all related. Yeah.
Yeah.
All right. So I'm going to have to bounce back and forth because Verge is having printer issues with her black ink. My printer doesn't want to print graphics, and I think it has to do with the fact that I don't have color ink in it, but I only have black and white. And a PDF file is actually a graphic. So I'm going to show you the problems we're doing, and then I'm going to have to hop over to the paper to work it. I think number 6 we can do on screen though.
Oh, definitely.
And this is called, you can see the tab up there, I'm sure. This is called 8.3 practice. It is a non-calculator activity made of non-secure problems off of AP Central, or not AP Central, sorry, AP Classroom. Some of them are multiple choice, many of them are free response. It's a mixed bag. And they've been retyped, a couple of them have been rephrased, so it does say adapted. So for number 6, we have a function f of t gives the rate of evaporation of water in liters per hour from a pond, where t is measured in hours since 12 noon. Which of the following gives the meaning of the integral from 4 to 10 of f of t dt? So again, focus on the unit analysis. I love doing what Verge was doing. So f of t is our rate of evaporation, and that is in liters per hour.
Yep.
And it's with respect to time, and time is in hours. So liters per hour multiplied by hours, the hour units will evaporate, and we get liters. So our final answer is in liters. So as I start looking at choices here, total volume in liters, net change in liters per hour, average rate of evaporation in liters per hour, I think I can take C, D, and E out.
I agree.
Because our units need to be liters. And then it's from time 4 to time 10, and those are hours after noon. So 4 p.m. to 10 p.m. So I'm looking at B as my answer. And I don't know if you agree with me or not.
I did. I got all of these right, actually, or at least the same answers as you.
I was really worried about this key because they are not in the same order. We selected them from AP Classroom for spacing purposes. And so I really expected to get an answer in the wrong slot.
Well, I worked them all just and then checked. You know what I mean? So,
Yeah.
well, I don't know how people teach by themselves. Like we're so lucky to have each other. My gosh. Oh, I love this question. Are we doing a picnic?
This is number 9. Yes, the picnic.
Picnic.
Where did that is from something.
Oh, come on now. Picnic basket.
Oh, it's Yogi.
Yeah.
I actually have a math shirt with Yogi in front of a Cal 3 problem because he's smarter than the average bear. It says the rate at which ants arrive at a picnic is modeled by the function a, where a of t is measured in ants per minute and t is measured in minutes. The graph of a for t from 0 to 30 is shown in the figure above. How many ants arrive at the picnic during the time interval from 0 to 30? So I am gonna slide on over to my camera now. And I don't have that graph anymore, but it's pretty easy to reproduce. We've got an x-intercept at 30, y-intercept at 4. So I guess we'll call that 15, 5, 10, 20, 25. It's at 10, 8. And then it's just line segments. And this is A of t. And I hope that's big enough. I'm kind of flying. Okay, thank you. It says, and A of t is the rate of arrival of ants. And it says, how many arrive? So if I integrate the rate with respect to time, this would be ants per minute times minutes. That should tell me how many ants are there as long as I integrate from 0 to 30. And so you're like, but we don't have to do rate-in problems on this year's AP exam. But you know what we do have to do? Be able to find a definite integral, even when not given the function explicitly. So once again, we're finding these areas. And I don't know, do you do this as a trap or do you break it?
Well, the way the graph was presented, me personally, I would probably just like be each box is worth 10.
Yeah, that's a pretty good way to do it.
Yeah, like that's just how I do it. But you know, it's however your mind goes first, I would say. You know, if you want to break it into a trapezoid and a triangle and add those two together.
Yeah, so what Verge is saying is this is 5 by 2 on every box. So these are all 10s, which means those are 5s, right?
Yep.
So
Which means
5,
they make a
10,
10.
15, 20, 25, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 140.
Yep. That's
That looks
correct.
like D.
Yep.
That we're looking at.
Mm-hmm.
Ooh, highlighted the whole row. Oh, that's not good. Okay, so we're not going to try and highlight it.
It's
Right.
D. It's
It's
D as in
D.
dinosaur. Yep.
All
It's
right.
a great question, and it's definitely something that you like Mark said, to be able to interact with something where you don't actually have the formula that you can differentiate or anti-differentiate, having that conceptual understanding of what's going on is always huge every year, and I think it's going to be definitely huge this year. So,
Yeah. And
yep.
and again, for those of you that are wondering, well, but we're not going to have multiple choice. We're not going to have rate in. Well, what if I asked you to integrate? I just said this was a picture of A of t, and I asked you to integrate A of t from 0 to 50, and then I give you 30 to 50 as a piece algebraically.
Mm-hmm.
So now you'd have to integrate that one using fundamental theorem and add this 140 to it. So these are all skills that could show up. I don't think
Mm-hmm.
we're doing anything that is a misuse of our time or
Mm-hmm.
yours, the
Mm-hmm.
viewer. Okay, I'm going to blow this up. We're looking at number 5 now.
Mm-hmm.
And we have a table. It looks like the table has T on top and R prime on the bottom. And bear with me while I organize my desk space.
Yeah, I
All
could
right.
read it if you want me to.
That'd be awesome.
Okay,
I'm going to copy down the information I need.
Okay, yeah. So the volume of a spherical balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of t, where t is measured in minutes. Selected values of t on this interval from 0 to 12 and corresponding values of r prime of t are shown in the table above. The radius of the balloon is 30 feet when t is equal to 5. Note, the volume of the sphere radius r is given by v equals 4/3 pi r cubed. Also note, that parentheses stuff is not needed for what we're asking. This actually,
also noted.
If I'm remembering correctly, this is a free response question from several years ago, maybe even on a practice exam. I honestly don't remember exactly, but this what we're about to ask, and I'm about to read it out loud, is one of the 4 prompts probably that really dovetails nicely with this skill. So use a right Riemann sum with the 5 subintervals indicated by the data in the table to approximate this definite integral from 0 to 12 of r prime of t dt. Using correct units, explain the meaning of this definite integral from 0 to 12 of r prime of t dt in terms of the radius. So pulling everything together.
Yeah.
Now we're going to have to do a Riemann sum.
So
I think it said right Riemann sum.
yes, and I did copy that. Can you see my screen now?
It looks awesome.
I didn't want you to rate it. I just want to make sure you could see it.
I can see it.
Excellent. Okay, so I have my table copied down, my distractor information, because this was a multi-part problem. And T is 5, R is 30, and R is twice differentiable. But they want me to use a right Riemann sum to find and then interpret this integral. So here's your review of right Riemann sums,
which we will review a lot more later. But
oh yes, we're going to have a whole day on tabular
this is
problems.
your little sprinkling of it to kind of get it going for
so
you.
It says there were 5 subintervals, but there are 1, 2, 3, 4, 5, 6 data points, right? So we've got this interval, which has a width of 2, a width of 3, a width of 2, a width of 4, and then from 11 to 12 is a width of 1.
So he's just subtracting to
from
get
0
those
to 2
widths.
is a 2. Sorry, camera's attached to my paper. So these are my delta x's, if you want to think of them as 2 and a jump of 3 on t, sorry, delta t, a jump of 2, a jump of 4, and a jump of 1. And they want the right hand. And when I started teaching, I always used to draw this. And then I realized I was wasting a lot of time. Well, I take that back. It's not a waste of time if it helps and you need to get started. But if I'm doing a right Riemann sum, then for this pairing, I'm going to use the right number. And for this pairing, I'm going to use that number, that number.
And when he says the right number, he means the number on the right-hand side of the interval.
Yes, left.
As opposed to the wrong number.
Right, not left. Both could be correct. And they both could be wrong if you're doing a midpoint. So yes, that's a very good point, Virg. Thank you. Or several points. So I am going to do this as it is. I'm going to do some. I'm not going to spend a lot of time on sigma notation, but just for myself, I'm doing the sum of the widths and the heights for these 5. So my first width is 2. I'm going to multiply that by a height of 4, a width of 3, multiplied by a 2 multiplied by a 1.2, a 4 times a 0.6. I would actually write 0.6. I'm really bad about leading zeros. Any of you that do number sense and UIL will understand. It's the Texas academic contests. And then this looks like 8 and 6 and 2.4 and 2.4 and 0.5. 4.8. So these, if I'm just showing you mentally what I do, this is 10.8 plus 5 is 11.3 plus 8. Is it 19.3, Virg?
You know, I was just looking at my stuff. Hang on one second.
I don't want to write it till it's right. I have an eraser, but I don't want to use it.
This is the balloon problem.
5.
Number 5. Hang on a second. Number 5. Dang it.
I'm feeling pretty good about that.
What did you say? 19.3?
Yeah.
Yep, that's what I have.
Whew. All right. So now, what do we have to show on a free response on an FRQ, right? We'd have to show. We'd get to stop here for the Riemann sum. That's a numeric answer, right? But doesn't make sense in real life. Units on this 19.3. Well, we're doing feet per minute. Feet. That's a unit. Okay.
Foots per minute.
Yes. Fifth per minute. Times minutes. Those cancel. So whatever this represents is 19.3 feet. R prime is the change in our radius, correct?
Yes.
So I would say from time 0 to time 12 minutes, and you cannot see what I'm writing. So let me zoom out. My super advanced zoom where I physically lift the camera. From time 0 to time 12 minutes. And they said they wanted this in terms of the radius. So I don't want to say that R prime, anything happened to R prime. I want to talk about the radius. Increased 19.3 feet.
Nice.
I suppose if I really want to, I could say it increased, oh no, that was at 5 anyway. So I don't even know what it was at 0. So I'm good.
Yeah, that must be for a different part of the problem.
Yeah.
Which we will probably unearth at some point.
Yeah, exactly. So, all right. And
then number 3, I think you wanted to do next, right?
Yes, we're going to go to number 3. Oh, no diagram.
Yep.
So we have Snowfall.
No table, no diagram.
But this is not the famous Janet problem. There is a Janet Snowfall problem, which notorious may be a better word. It says snow is falling at a rate of R of t equals 2 times e to the negative 1/10 t inches per hour, where t is the time in hours since the beginning of the snowfall. Which of the following expressions gives the amount of snow in inches that falls from time t equals 0 to time t equals 5? So again, I'm going to switch you back over to my camera.
And I think as Mark's kind of getting set up, I do want to say that when we're practicing a bunch of these problems of this type, it's really easy, like, oh, I'll just set up a definite integral, blah, to blah, to blah. But realistically, when everything is scrambled together, it's hard to know, should I be taking the derivative? Should I be anti-differentiating? What should I do? And one clue that I always tell my students is, if you have the rate and you're being asked about an amount, you should set up an integral, a definite integral. What about you, Mark? Oh, look at how clever you are.
Yeah, I decided I'm going to take a risk. And I know now you guys can see I've got Blender on my shortcuts for those of you that know what Blender is. But I decided this would be better than trying to talk back and forth. So we've got our R of t is 2e to the negative 1/10 t, and that's the rate, right? That is a rate. And we want to accumulate it. We want to know how much snow fell from 0 to 5. And before I continue, I do want to do a little small unit analysis. Inches per hour times hour. This will get me inches. And they have set up here the amount of snow in inches. So I'm at least getting the right numbers. I'm going to bring the 2 out here. I'll leave myself a little bit of space. Absolutely, you can set this up with a u is negative 0.1 t and play that game. I'm going to pull the Julia Child version again. The chain of that is negative 0.1. And I'm going to offset that by dividing by negative 1/10 as well. So if I multiply these together, I still have my original function. But right now, negative 1/10 dt is the derivative of negative 1/10 t. So that's your u and your du. You can actually, for those of you that prefer that method. I just wanted to jump to.
And my students would probably hop as well because they know the integral of e to the kt dt
Right.
would be equal to 1 over k e to the kt plus c. So like that's that yellow sheet again. Like we would have established that and put that on our yellow sheet. And so this is fitting that form. I love the way Mark slid that 2 out front because that helps you really see that the negative 0.1 is that k value.
Ooh, that is not in focus.
It's good. It's good.
Okay.
It's getting there.
So
okay.
we plug the 5 in, plug 0 in. E to the 0 is usually 1.
In this universe.
Yeah, on Wednesdays in April. And there's my final answer. That is in inches. And it looks like that might be choice D, except I have a sign error.
What? No, you do not. Huh.
I do, because I didn't subtract a negative.
Oh, Mark.
Subtract negative plus.
Well, you're lucky that that wasn't an answer choice.
I am really good at this. My kids who have me for my PSAT prep class know that when I make mistakes, I make unique mistakes that are not anticipated by the multiple choice writers, and that is a skill. It has served me well.
Yeah, that is good.
So
lucky.
Number 1. Oh, do we want to do number 1?
Well, we're kind of getting
we're
close
at 3 minutes. You know what? I'm going to leave that.
Okay, or we could maybe start it, and I don't know. What do you think?
I think whichever decision we make is the right one. Because what else are you guys going to do than listen to us chatter away?
I don't know if that's true based on our
Don't close the tab.
analytics.
Don't close the tab. Yeah. So the only thing I would say is I'm going to leave this for you guys. It's the first one in the worksheet. But something to note, this, the initial condition, if you look down here, the initial condition is actually the value of the function at 8. So as you look at this as an accumulation model, and this is f prime, so it's an accumulation of change in f, you're walking backwards. So the function from this point, which looks like 6, from x equals 6 to x equals 8, f grows 7 units. So when you're walking backwards, you're going to want to walk down 7 and so on. And again, this one has a little more information than you might need because it's the stem of a free response that had multiple questions, but you're just trying to determine the absolute minimum. So this is an extreme value practice for you guys.
And I would suggest making a table. That's usually how I do it. And I would put like 8, 4 on the table, kind of low down. And then all my critical points would be, I'd put like 0, 1. What do I see there? What is that? A 4?
It's
0.
5. 4. No, you're right. Because 3, 4 is the peak. Yeah.
Yeah.
So 1, 4, 6, and 8. Yeah.
And yeah, so we'll leave this for you guys. There's lots of problems like this also on the circuit where you can examine the minimum or the maximum based on the information and stuff like that. So what else, Mark?
Again, connectivity. Thanks for coming. That activity, the circuit that Verge was working, are both in the Dropbox already. And I'm going to put the key for that and the 2 slides from the warm-up are going to go in the Dropbox while we debrief with our producer in a few minutes.
Yeah, so again, yes, thanks for coming. And we really enjoy getting these lessons together for you, and enjoy the fact that so many of you are getting so much out of these lessons. So thanks a lot. We appreciate you.
Bye, guys.
Bye.
Bye, sons.
What am I going to do with him?